Welcome to Party, May 17th, 2026. Here's a question that should genuinely unsettle you. What if the act of installing a software package didn't just run code? It turned your machine into the next weapon in the attack? Not a theoretical scenario, not a proof of concept. Something that has now happened 3 distinct times in an escalating campaign that has compromised over 1,000 open source packages, hit organizations like Zapier, PostHog, Postman, Tanstack, and Mistral AI, and earned a CISA advisory. The campaign is called Shai-Hulud, named after the giant sandworms from Frank Herbert's Dune. And the name is disturbingly accurate, because like the sandworm, this thing moves under the surface. It's massive, and by the time you see it, it's already on top of you. Today we're going deep on what is, in my read, one of the most technically sophisticated and structurally alarming supply chain attack families we've seen in the open source ecosystem. Let me set the stage, because to really understand why this campaign is so dangerous, you need to understand the world it's operating in. NPM, the Node Package Manager, and PyPI, the Python Package Index, are the 2 largest open source package registries in the world. Collectively, they host millions of packages. And here's the thing, most people don't internalize. When you install a package, you're rarely just installing one thing. You're installing that package plus all of its dependencies, plus all of their dependencies. Recursively, we call these transitive dependencies. And in a typical web application, you might have hundreds or thousands of them that you've never looked at, never audited, and probably couldn't name. It's like ordering a sandwich and trusting that every ingredient in the bread, the condiments, and the wrapper is safe, without ever seeing the supply chain behind any of it. That's the trust model NPM and PyPI run on, and it's the attack surface Shai-Hulud was built to exploit. Now, GitHub Actions is the other piece of infrastructure you need to understand here. It's the dominant CI/CD, continuous integration and delivery, automation platform. Basically, it's the system that automatically runs tests, builds software, and publishes packages to NPM and PyPI whenever a developer pushes code or merges a pull request. The vast majority of popular open source projects use it. And GitHub Actions has this permission model that is, I'll be honest, genuinely confusing even if you know what you're doing. There are 2 workflow triggers that sound almost identical: pull request and pull request target. The difference is subtle but catastrophic. The pull request trigger runs in an isolated, sandboxed context. It doesn't have access to secrets. It can't publish packages. It's essentially quarantined. The pull request target trigger, on the other hand, runs in the base repository's privileged context. It has access to secrets. It can publish packages. It's trusted. And the whole point of pull request target is to allow workflows to do useful things like post comments on pull requests from forks. But if you're not extremely careful about what code you let run in that context, you've just handed an attacker the keys to your entire publishing pipeline. Here's what most people get wrong about this. The vulnerability isn't a bug in GitHub Actions. It's a design feature that's been misunderstood at massive scale. Security researchers documented this attack class. They call it a Pwn Request. Back in 2021, GitHub published guidance on it. And yet here we are in 2026, and it's still being exploited across thousands of open source repositories because the workflow trigger names are confusingly similar, and the security implications are genuinely non-obvious unless you've specifically studied this. That's not me being harsh on developers. That's me saying the ecosystem has a systemic education and tooling gap that attackers are actively farming. The other piece of infrastructure worth understanding is OIDC tokens, OpenID Connect tokens. These are short-lived credentials that GitHub Actions can issue to authenticate to external services, like NPM's registry. They replaced long-lived static secrets, which was an improvement, but short-lived doesn't mean safe if stolen. If an attacker can intercept an OIDC token during a workflow run, they can use it to publish packages as a legitimate maintainer. That's the crown jewel in this entire attack chain. So, with all of that context in place, let's talk about the campaign itself. because it has a versioning history, which is one of the details that stands out to me as particularly alarming. The original Shai-Hulud worm compromised over 500 NPM packages. That was significant enough that CISA issued an advisory about it. The CISA alert describes the worm gaining initial access, then deploying malware that scanned the environment for sensitive credentials. And here's where the self-replicating mechanic kicks in. Those stolen credentials were used to compromise additional packages, which then stole more credentials, which compromised more packages. It's not just a supply chain attack, it's a supply chain attack that reproduces itself. You don't need the attacker to manually go find the next target. The malware does it for them. That's what makes the worm designation accurate, and not just marketing language from the security community. Then, on November 24th, 2025, the community identified what got dubbed Shai-Hulud, and based on the reporting I've looked at, this wasn't just a repeat, it was a genuine upgrade. The 2.0 version introduced more automation, faster propagation, and a broader target set. It backdoored 796 unique NPM packages. That's a 50% increase over the original campaign in terms of raw package count. And the targeting strategy was deliberate. The attackers went after high-profile maintainer accounts from organizations like Zapier, PostHog, and Postman. Why those? Because packages from those organizations have enormous downstream footprints. If you compromise a Zapier NPM package, you're not just hitting Zapier, you're hitting every developer and every CI/CD pipeline that depends on anything Zapier maintains. My take is this reflects a calculated blast radius optimization strategy, not random opportunity. The attackers were thinking about leverage. The technical detail that I find most alarming about Shai-Hulud 2.0 is the pre-install hook mechanism. NPM packages can define lifecycle scripts, little bits of code that run automatically at different stages of the installation process. The pre-install hook runs before anything else, before your tests, before your security scanners, before you've had a chance to inspect anything. So when Shai-Hulud 2.0 injects malicious code into the pre-install phase, it's not just hiding in the package, it's executing before the tools you'd use to detect it have even had a chance to run. That's a genuinely clever abuse of a long-standing NPM design decision. And PyPI has analogous mechanisms. This isn't a new attack surface. The security community has flagged lifecycle hook abuse for years, but seeing it weaponized at this scale in a self-replicating worm is a qualitative escalation. If you're a developer and you haven't thought about what happens during NPM install beyond it download stuff, this is the moment to update that mental model. Now we get to the third iteration, and this is where the technical sophistication really becomes apparent. On May 11th, 2026, according to reporting from SNEC and others, a threat actor group called Team PCP launched what's being called Mini Shai-Hulud. And the mini is a little misleading because while the raw package count is smaller, 84 NPM package artifacts across 42 packages, the attack chain is more technically intricate than anything in the previous iterations. The targets included the entire TanStack namespace, plus packages from Squawk and Mistral AI, ultimately affecting over 160 NPM and PyPI packages combined. Headlines I've seen frame this as Team PCP using hijacked GitHub OIDC tokens to spread a credential-stealing worm through TanStack NPM packages. And that framing is accurate, but it undersells the elegance of the exploit chain that got them there. Let me walk through the TanStack attack chain, because TanStack has published a detailed postmortem, and this is worth understanding step by step. TanStack, the project behind React Query, React Router, and a bunch of other foundational React ecosystem libraries, had a GitHub Actions workflow that used the pull request target trigger. That's step 1, the misconfiguration. Step 2, an attacker submits a pull request from a fork. Because the workflow uses pull request target instead of pull request, that PR triggers execution in the base repository's privileged context. The attacker now has code running with elevated permissions. Step 3, and this is the clever part. The attacker uses this privileged execution to poison the GitHub Actions build cache. The cache is a shared resource that workflows use to speed up builds by storing things like downloaded dependencies between runs. By writing malicious data into that cache across the fork-to-base trust boundary, the attacker sets up a trap for the next privileged workflow run. Step 4. That poisoned cache gets consumed by a workflow that has access to OIDC tokens. The tokens get stolen. And Step 5. Those stolen OIDC tokens are used to authenticate to NPM's registry and publish Trojanized versions of TANstack packages that contain credential-stealing malware, which then scans victim environments for secrets to fuel the next wave. I want to pause on the cache poisoning step, because I think it's the most underappreciated part of this chain. GitHub Actions caches are scoped to branches, but there are edge cases in how fork-to-base cache sharing works. And the Pwn Request attack class exploits those edge cases to bridge the trust boundary. Essentially, the attacker is using a workflow run they control, the forked PR, to write data into a cache slot that a later trusted workflow run will read from. It's like leaving a poisoned water bottle in a shared kitchen fridge and waiting for someone with a higher security clearance to drink from it. The individual pieces, the cache, the OIDC token, the NPM publish step, all look legitimate in isolation. It's the chain that's malicious. And that's exactly why automated security scanning often misses this class of attack. Each individual action looks fine, but the composition is the exploit. Now, why does the TANstack compromise specifically matter at a scale beyond another NPM attack? Because TANstack packages are foundational dependencies for a huge fraction of the React ecosystem. React query alone has tens of millions of weekly downloads. React Router is used in an enormous percentage of React applications. When those packages get Trojanized, even briefly, even before being pulled from the registry, every developer who ran npm install during that window, and every CI/CD pipeline that built during that window, potentially ran credential-stealing malware. And here's the compounding problem. Those credentials, NPM tokens, Cloud API keys, GitHub tokens, can then be used to compromise other packages, other pipelines, other organizations. The victim doesn't just suffer the initial compromise, they become a potential vector for the next. The post-mortem TANstack published is worth reading in full. They document both what happened and the organizational changes they're making, including a companion hardening guide. I'll link to that in the show notes. I also want to bring in a separate but thematically connected development, because it reinforces the broader point I'm building toward. There's been a reported QEMU FegVM hypervisor escape exploit. QEMU and KVM are the virtualization technologies that underpin a huge amount of cloud and CI/CD infrastructure that allows root code execution on the host system. So, not just inside the virtual machine, but on the physical host running the VM. Now, this is a different technical domain from the supply chain attacks we've been discussing, but my read is that it belongs in the same conversation because it illustrates the same fundamental pattern. The isolation boundaries we rely on are not as robust as we assume. Whether it's the package registry trust model, the GitHub Actions permission boundary, or the hypervisor layer separating tenant from host, each of these is an abstraction that can collapse when an implementation flaw is discovered. If your CI/CD build infrastructure runs on shared VMs, a hypervisor escape means an attacker who compromises a build job can potentially escape to the host and affect other tenants. That's not a theoretical concern when you're already dealing with a worm family that's actively targeting build pipelines. There's one more force multiplier I want to address, and it's the AI angle. The research brief I've been working from flags AI-accelerated vulnerability research as an emerging element in this threat landscape. And I think it's worth being precise about what that means. Large language models and automated reasoning tools are reducing the time and expertise required to do several things that previously required significant human skill. Discovering exploitable misconfigurations in CI/CD workflows, analyzing package ecosystems to identify high-value targets, and generating functional exploit code. The Pwn Request attack class is a perfect example of something that benefits from this acceleration. The vulnerability pattern is documented. GitHub published guidance on it in 2021, but identifying which of the hundreds of thousands of open-source repositories on GitHub have this misconfiguration, and which of those have sufficiently high-value downstream footprints to be worth targeting, is exactly the kind of large-scale enumeration and prioritization task that AI tooling is good at. I'm not saying Shai-Hulud was built with AI. I'm saying the barrier to industrializing this attack class is lower than it was 2 years ago, and getting lower. Let me talk about implications now, because I think the full picture here is more alarming than any individual incident. What the Shai-Hulud campaign family demonstrates is that the attack surface for software supply chains now spans the full stack. At the top, you have package registry authentication, OIDC tokens, maintainer credentials, publish permissions. In the middle, you have CI/CD workflow logic, GitHub Actions configurations, cache scoping, permission models. And at the bottom, you have the infrastructure layer, the VMs and hypervisors running the build systems. The QEMU is a reminder that the bottom layer is not a given. And what's novel about Shai-Hulud specifically is the self-replicating architecture that connects all of these layers. A worm doesn't just steal credentials, it uses those credentials to compromise more packages, which steal more credentials, which compromise more packages. The attacker's initial investment multiplies autonomously. That's a qualitatively different threat model than a one-time supply chain compromise, and it demands a qualitatively different defensive response. The targeting strategy across the 3 iterations is also worth examining as a data point. The original campaign hit over 500 packages, broad but not necessarily strategic. Shai-Hulud 2.0 targeted maintainer accounts from Zapier, PostHog, and Postman, organizations with significant NPM footprints, suggesting deliberate target selection for blast radius. Mini Shai-Hulud went after Tanstack and Mistral AI, one of the most widely used React library collections and a prominent AI company. There's a pattern here of escalating strategic sophistication, not just technical sophistication. The attackers are thinking about downstream impact, not just immediate compromise. And the expansion from NPM only in the original campaign to NPM plus PyPI in Mini Shai-Hulud shows the ecosystem scope is growing. If you're a developer or a security team and you've been thinking we use Python, not JavaScript, so this doesn't apply to us, that assumption is no longer safe. The PyPI angle in Mini Shai-Hulud is a direct signal that the worm family is generalizing across registries. For organizations trying to figure out what to actually do about this. And I want to be practical here, not just analytical. There are a few concrete areas worth prioritizing. First, audit your GitHub Actions workflows right now for pull request target triggers. If you have them, ask whether the code running in that context could be influenced by a forked pull request. If the answer is yes, you likely have a Pwn Request exposure. The Tanstack postmortem and hardening guide are public and detailed. I'd start there. Second, look at NPM provenance attestation. NPM has introduced tooling to cryptographically attest that a published package came from a specific workflow run in a specific repository. If you maintain packages, publishing with provenance makes it significantly harder for an attacker to publish a Trojanized version without that attestation being absent or mismatched. Third, and this one is harder, think about runtime monitoring for package install hooks. The pre-install hook abuse in Shai-Hulud 2.0 is particularly nasty because it executes before most scanning tools run. There are tools that can monitor and alert on suspicious pre-install behavior, but they require deliberate adoption. Now, let me get into prediction territory. And I want to be explicit that this is pattern matching from the signals I've described, not first principles research or confirmed attacker plans, but based on what we're seeing. One plausible trajectory is that the Pwn Request attack class gets industrialized in a way that makes the Tanstack incident look like a manual artisanal version of what's coming. The tooling investment required to build an automated scanner that continuously enumerates GitHub repositories for pull request target misconfigurations, and then queues high-value targets for credential harvesting is modest relative to the potential yield. There are hundreds of thousands of open-source projects on GitHub. The TAN-stack postmortem is now a public, detailed, worked example of exactly how to execute this attack. If I were a threat actor with moderate resources and an interest in supply chain attacks, that postmortem would be required reading for my team, and I'd be building automation around it. The question is whether the defensive tooling, automated workflow scanning, mandatory provenance attestation, better default permissions, can scale as fast as the offensive tooling. Here's the contrarian take I want to leave you with on the prediction side, because I think it's genuinely underappreciated. The ecosystem registries are not static targets. NPM, PyPI, RubyGems, Crates.io, they're all actively investing in security improvements. NPM's provenance attestation is one example. PyPI has been hardening its authentication model. The registries know they're being targeted, and they have economic and reputational incentives to respond. So here's the dynamic I'd watch. If the worm family expands to RubyGems or Crates.io or Maven Central, which the expansion from NPM to PyPI suggests is a plausible next step, the question isn't just will it happen, but will those registries have implemented sufficient provenance and authentication controls by the time it does? The race between offensive capability and defensive infrastructure is the actual story here. And right now, based on what we're seeing, the offense has a meaningful head start. But registries that move fast on provenance attestation and token scoping could close that gap faster than people expect. That's reading signals, not certainty. So let me close by pulling the thread all the way back to where we started. At the beginning of this episode, I asked, what if installing a package turned your machine into the next weapon in the attack? That's not a hypothetical. That's the documented behavior of Shai-Hulud 2.0 and mini Shai-Hulud. The pre-install hook runs. It scans your environment. It finds credentials. Those credentials get used to compromise more packages. You never see it happen. Your security scanner never flagged anything. And now you're part of the worm's propagation chain. The thing that makes this campaign family genuinely alarming, beyond the raw package counts, beyond the high-profile targets, beyond the CISA advisory, is the self-replicating architecture combined with the strategic targeting of high-value maintainers. It's not brute force. It's leverage. And the attack surface it exploits spans the full stack, from the trust model of package registries through the permission model of GitHub Actions to the isolation model of the hypervisors running the build infrastructure. If you're watching this in 2026, you're going to look back and remember exactly when supply chain security stopped being a niche concern and became a foundational assumption that every development team has to carry. We're in that moment right now.